Hello guys, welcome to Origins computer classes once again. See, in my previous video I have already discussed about the bubble sort and the basic and its basic concepts, how it works, and including the code of the bubble sort, right? So today in this lecture we will be discussing some of the important questions that may come in bubble sort, and also some of the concepts which I assume that many of us don't know. Okay, so first concept is that order of bubble sort. Okay, now what do I mean by order? So that is, there may be a question that can come in your exams whether bubble sort is stable or not. So what does stability mean? So say suppose I am taking an array. So say it is an array named A and it is having say 5 elements like this: 1 2 3 4 and 5. 1 2 3 4 5 0 1 2 3 4. The indexing is so done, and we are having certain elements, say 5. Then we can say we have 70 here. Okay, and we can have, say, okay, let me take a smaller element, not 70. Say suppose here we have 30. Okay, and we have, better let me take another length because we need to consider the stability. So say here we have 120, here we have 120 in green color. Okay, then next we have say another 20 in red color, and next we have some another 20 blue color. Okay, and at last we have another element, say suppose say it is say 7. Fine. Now what does stability mean? By stability we mean to say, even after sorting, the position of these 320s, the order of these 320s should remain stable. Like here in the unsorted array, the original array, we have green 20 first, then we have red colored 20, then we have blue colored 20. After sorting, after sorting also we must get green 20 first, then red 20, then blue 20, right? And it doesn't matter how they come, but the green 20 should be first, the second red 20 should be second, and the blue 20 should be at last, and the whole array sorted. So if that happens, then we can consider this sorting technique to be stable, right? So let us first go through the code. If we go by the code, then we have, say here I am writing the code in a separate site. So for I equal to 0, I less than say n is the size of array. Here n is equal to 6. Okay, and I plus plus, opening brace, for j equal to 0, j less than or equal to n minus I minus 1. Hope you have watched my previous video. I guess these concepts are not new to you. If this seems new to you, you may please go to my videos, search bubble sort by Origins classes at the Origins classes, and watch my first video on bubble sort. That is the part 1 video. This is my part 2 video. Okay, so j plus plus, okay. Opening brace, if a of j greater than what it is, a of j plus 1, then we have temp equal to a of j a of j equal to a of j plus 1 and a of j plus 1 is equal to 10. Fine. Closing of loop. Okay, another thing. So that swapped equal to 0. Swapped equal to 0 because we are considering the optimized form of bubble sort, right? Optimized form of bubble sort. Swapped equal to 1. If swapping happens, then we should make it 1. Closing of j, if swap equal to 0, then we can terminate. Fine. So that is for the best case, right? When the entire array is sorted, only once j loop will run, so the time complexity is big O of n because the j loop will be running once and then it will be terminated. Now, so by this concept, let us now check with this array if bubble sort is stable or not, right? Okay. So now first pass, when I equal to 0, first pass I is equal to 0. So 5, when j equal to 0, j is equal to 0 at now. Now, if a of j greater than a of j plus 1, so 5, is 5 greater than 20? No. So they are at their correct position, so no swapping required. J moves to the next index. J moves to the next index. Okay. Now 20. Is 20 greater than 30? No. And 20 is placed before 30. So therefore no swapping is required. Therefore j moves to the next index. 30. Is 30 greater than 20? Yes. So should 30 come before, should 30 come before 20? No, because 30 is greater than 20 as per the rule of ascending order. We must have 30 after 20. So therefore 30 must come after 20. Okay. So the swapping is done here. This is 20. Right? So, and now 30 again. 30 is 30 greater than 20? Yes. So should 30 come after 20? Yes. So therefore swapping is required. Fine. So 20 comes before and 30 comes after. The elements are swapped. Again, is 30 greater than 7? Yes. Should 30 come after 7? Yes. 30 is greater than 7, so as per sorted. So 30 comes after 7. So this is fine. Modified. So j reaches the end of array and j should go up to, because this is first pass, I equal to 0. So j is less than equal to 6 minus 0 minus 1 up to index 5. So up to index 5 j has moved. And at the end of the first pass, if you observe, we have the elements like say 5. Then we have here 5, 20, 7. And element 30 is at its correct position now. That is the heaviest element that moves to the rightmost part. Okay. So this part at the end, this portion is sorted, is being sorted. and this is at the end of the first pass. So after at the end of the first pass, this is the result we have, right? Now again, if you see, so we begin with our second pass, right? When the after at the end of the first pass, second pass begins. So when second pass begins, I equal to 1. J again starts from the beginning here. Now up to which index now J should move? Obviously up to 4, because n minus n is 6, 6 minus 1 minus 1, so up to index 4 J is going to move. Now 5, is 5 greater than 20? No, so therefore no swapping required, J moves. Is 20 greater than the 20? No, they are equal, so no swapping required, J moves. Again, is 20 no, 20 is not greater than 20, therefore J moves to the next index. Again, is 20 greater than 7? Yes. And is 20 placed at its correct position? No, therefore 20 should come after 7, right? So let me erase this. 20 comes after 7. Okay, 20 comes this. Now J moves here. So is 20 greater than 30? No, and as 20 is less than 30, so they are placed at the, so actually we don't need to compare, J has reached the end actually. Extremely sorry, because J less than equal to n minus, so actually J has reached the end of comparison, because after first pass, in second pass we must go up to 4. So after the end of second pass, the modified array which we are having is 5 and somewhere here 7 at index 3, 20, up to this portion it is being sorted after the second pass. 20 and 30 are at their correct position, right? It's my bad. Let me mark it as blue because we are just checking the order to the right. Now again, so at the end of the second pass, this is what we are left with, and J will again begin at the beginning of the third pass, that is I is equal to 2. J will go up to index 3, right? Because n is 6, 6 minus 2 minus 1, so that is 3. 6 minus 2 minus 1, the result is 3, so 0 to 3. Now, so J again starts comparing, is 5 greater than 20? No, 5 is less than 20 and it is at its correct position. J moves to the next index. Is 20 greater than 20? No. Therefore, J moves to the next index. No swapping required. Is 20 greater than 7? Yes. So therefore, swapping is required and 7 moves here. Fine. And now this is our J. And therefore here the second pass ends because J has reached the end of comparison, because J must move up to 3 in the second pass, and so up to this portion it got sorted, right? So therefore I am just not rewriting it because there are no space, because I have to show you here the fourth pass also. Okay, let me rewrite it for you. 5,
then 7. Just a second.
okay. So this is at the end of our third pass. After at the end of third pass, this is our resultant, right? So at the end of second pass, elements were sorted. At the end of third pass, so these three elements have been at their correct position. Now the fourth pass begins. So at the fourth pass, when I is equal to 3, fourth pass, when I is equal to 3, what happens? So the comparison will be up to index 2, right? Because 6 minus 1 minus 2, I mean 6 minus 3 minus 1, so 4. 6 minus 4 is 2. Therefore, now, so 5 is 5 less than 20? Yes. So 5 is placed at its correct position, no need to swap. Therefore, J moves to the next index. 20, is 20 greater than 7? Yes. Is 20 placed at its correct position? No. So we need to swap it. Therefore, 20 comes here and 7 goes here and J moves to its next index. So now this is the end of our fourth pass and we are remaining with this result actually, where 5, 7 and here we have 3 20s. So here we have 30, 0, 1, 2, 3, 4, 5. Okay, so what happens here? 20, then we have say another 20 with red, and here comes another 20. Now do we need to check any more pass? See, after fourth pass, if J again begins comparison for fifth pass, there will be actually another time J will be comparing. But see, if you observe this array carefully, there will be no swapping required at any instant. See, if I check 5, is 5 greater than 7? No. Is 5 placed at its correct position? Yes. Therefore, J moves to the next index here. J moves to the next index. Is 7 greater than 20? No. And is 7 placed at its correct position? Therefore, yes. And therefore, J moves to the next index. Same, 20 is never greater than 20. So, J will gradually move to this index. And finally, of course, this is sorted. So, if you see, at no point there is a time when it can enter this if condition, right? Because every time this if condition becomes false, a of j greater than a of j plus 1, and this swapped remains 0. This variable swapped remains 0. See here, there was at least 1 or 2 swaps that we have done, right, during these passes. Therefore, swapped turned 1. It could enter this if condition now. Therefore, this swapped turned 1. But here, the swapped remains 0. And so, if swapped remains 0, then the loop terminates and we come out of the I loop. So, therefore, this is the final sorted array. Now, if you observe, in our original array, green 20 comes first, red 20 comes second, and blue 20 comes last. And the same happens in our sorted array also, right? See, the green 20 comes first, the red 20 second, and the blue 20 last. So can we say that bubble sort is stable? Yes, because the order of the elements are maintained, right? Order of, if there is a repetition of elements, there is some repetition, then the order of the elements are maintained. Therefore, point number 1, I hope I can remove this code. You have copied this. This is also present in my previous video. So point number 1, bubble sort is stable. Bubble sort is stable, right? Now, another question that usually comes in exam is, first the things are that what are the best case and worst case time complexities of bubble sort. Now see, best case. So what is the best case that we can consider? Now if the entire array is sorted, now if the entire array is sorted, as you can see here, 5, 7, 20 all are sorted. Now the J loop for at least one time from checks from 0 to some n minus I minus 1 times. So it is approximately n, because n minus I minus 1, if n value is very large, say about 10,000, 20,000 or something, so that I value may be sometimes negligible, right? Because index 3, index 4, index value. Therefore, what happens? J compares, J at least up to the end of the ending length of the array, J moves, right? In order to check if the array is sorted. So, but the external loop, as the array is sorted, swapped remains 0 in optimized bubble sort, I am saying, not in case of the usual bubble sort that we have, where the swapped variable is not present. If the swapped variable is present, so the entire outer loop terminates after the J has done its comparison. Therefore, as the J moves for n times up to the length of array, we can say the best case time complexity of optimized bubble sort, of optimized, the non-optimized one is always big O of n square. Okay, the non-optimized one. But in case of optimized bubble sort, the best case time complexity becomes big O of n. Fine. Now worst case. For optimized one. Okay. Now worst case is definitely we can consider, say if the array is present in reverse sorted, that means in descending order. So if there had been, so consider this array is present in the reverse order, right? If at index 0, I am drawing it here, say at index 0 we have 30, then we have 20, then we have red 20, okay, then what we have is, say, green 20, 7, 5, green 20, and then we have 7, 5, 0, 1, 2, 3, 4, 5. Now here, if you see, the J loop moves, and every time J loop has to make one swapping. See, 30 greater than 20? Yes. And is 30 placed at its correct position? No. Therefore 30 and 20 we have to make swapping between them, right? So we can swap them. So 20 will come before 30, and again after that, even if the array is modified, so 30 comes here, again J have to make this comparison. So is 30 greater than 20? Is 30 placed at its correct position? So no, again we have to make swapping. So J loop has to continuously run, right? And every time at each pass, there can never, the swapped can never become, I mean what to say, never, swapped will always become 1, right? This swapped variable can never remain 0. Okay, therefore, as we require all the passes and J is moving at least up to n minus I minus 1, some negligible index. So it is near to n, J is moving up to some nearest value of n. Therefore, worst case is big O of n square, optimized one. And average case, as I have shown you, this is the array. At least sometimes swapping is required, and some point swapping is not required. So average case is also big O of n square. Average case is also big O of n square. Fine. So these are the questions that can come in your exam. So they can ask you what is the best case time complexity of bubble sort, worst case. Sometimes in viva also they ask these kind of questions. Okay. Now the second another question that can come from bubble sort is, what are the number of comparisons we are making in case of optimized bubble sort. See, in case of non-optimized bubble sort, it is definitely n and n, means n times n, because if there is not n minus I minus 1, n into n, that is approximately n into n comparisons, n square comparisons, right? But in this case, there is a hack. Although the comparison although the time complexity in the worst case is big O of n square, still the comparison we have to say the exact formula, what we are getting after making the comparisons. So if you see here, when during the first pass j is moving up to the index 5, right? So what we can say, j is moving at I equal to 0. So I am erasing this, just say at I equal to 0, at I equal to 0, j needs to move from 0 to n minus I minus 1. That means n minus 0 minus 1, that is n up to n, j has to do n minus 1 iterations, right? So n minus 1 times. Now when I is equal to 2, what is j doing? J is moving up to n minus 1 minus 1, n minus 2 times. N minus 2 times. When I is equal to 3, j is moving up to n minus, say n minus 3, n minus 3 minus 1. Okay, n minus, sorry, this was 1. So j is moving n minus 1 minus 1, so n minus 2, and this is I is equal to 2. J is moving n minus 3 times. And when I moves up at the nth index, this is the worst case I am talking about. So j moves up to 0. Fine. That means no iterations j have to make. Say up to this portion of array is sorted, up to the second element, up to from index 1 to last portion is sorted. Then say, suppose if the value of n is 10, or say it is 11. So for 11, first j moves 11 minus 1, that is 10 times. When then second time 9. If n is 11, then j here moves up to 10 times. Then we can say it is moving up to 9 times when n minus 2, 8 times, and so on up to 0. Fine. Now, can we say that the total comparisons we are making is the sum of all these comparisons we are doing? The total comparisons we are making up to the end, where till the array is getting sorted, is the sum of all these, right? We are adding this all. We can get the number of comparisons, total number of comparisons we are making. So now can we say that we are doing the sum of n natural numbers actually? See here, when we are taking the example, if I add 1 plus 2 plus 3 plus 4 up to 10, right, up to 10, then we can say the sum is 55. 10 into 10 minus 1 by 2, right? So 10, that is 5 gets cancelled, sorry, 10 into 10 plus 1 by 2, right? So therefore 10 into 11, so the total sum becomes 55 from 1 to 10, right? So here also we can say we are actually doing sum of n natural numbers, and the number of comparisons we are making is n into n plus 1 by 2. So this is the number of comparisons we are making, So this is a total number of comparison in case of bubble sort we are doing. In fact, it is due to this reason the time complexity becomes big O of n square in the worst case, right? Because n into n is n square plus n. So n square is much greater than n. N is n can be considered as negligible to n square. So we consider the bigger order. Therefore, n square is the total time complexity of the bubble sort in its worst case and also average case, definitely. So this was all about today's class. These are some questions that can come in your exam, or this can be asked in your viva. Okay, nothing more than this can be asked. Okay, because there is nothing more in bubble sort. So that was all about bubble sort. In our next upcoming videos, we will be taking into consideration another sorting technique, that is the insertion sort. Okay, so till then, bye bye, take care of your family members. Thank you.